All right, so here we'll be proving that the function n, where n divided by 2 for all even integers, and where n belongs to our natural numbers, and negative n minus 1 over 2 for all odd integers where n belongs to natural numbers. It's a bijection. Bijection from the natural numbers to all integers. So to start off thinking about this proof, first thing that we can kind of do to break down the pieces is that we can think about our natural numbers in two different pieces. We have odd positive integers and even positive integers. And on the other hand, for all integers, the two main pieces would be positive and negative integers. So our goal is to map the elements of here onto the elements of here and cover everything and have a unique element in n mapped to a unique element in Z. So to satisfy both injectivity and surjectivity and thus have a bijection. So when we're thinking about it this way, we can approach it as mapping, say, one of the halves of our first set onto one of the halves of the second set. And that's kind of what we do with this function here. And that's what we're going to be breaking down in the proof. So start off, proof. Let's just reiterate, let n be an element of the natural numbers. So if n is an even positive integer, we can represent this as n equals 2k, where k belongs to the natural numbers. And since we're mapping the elements of n onto Z, we're only going to be considering natural numbers that we are plugging in here. So if we plug this back into the first section or first part of our function, we will get that 2k over 2 is the representation. So 2's cancel out here and we just get k. And in this way, all positive integers, or all even integers from n, map the positive integers in Z. So that's kind of the first half of our proof here. Similarly, if n is an odd integer, it's kind of, we're reusing the same variable, but for this part we have n as an odd integer, so forget about this for the what we chose n as. Now it's an odd integer. So if n is an odd integer, we can represent it like this: n equals 2k plus 1, where again k belongs to the natural numbers. And we're gonna plug this into the second part of our function here. Plugging this into the second part of our function, we get 2k plus 1 minus 1 over 2 with the negative sign in front. And as you can see here, the 1's are going to cancel out. You're just going to be left with 2k over 2 with the negative sign in front. 2's cancel out, left with negative k. And as you can see, now we have accounted for all the negative integers in Z by considering all the odd integers in M. So now we account for all positive and negative integers. And all positive and negative integers is just C, our set C. So now we can say for each unique n in the natural numbers, our function defines negative integers for odd positive integers and positive integers from even positive integers. So it's kind of the end of our proof here. We have accounted for both parts of Z, negative and positive integers, by considering the even and odd parts of N. And this is our proof here. So